I'm going to go through this problem to show you how I think about area integrals. So this is a picture of, it's like a map, and I have a river going through the middle of the map like this. Since this is a math problem, it just so happens that this river has a math equation to describe it. And I am calculating the area of these two land pieces, this one plus this one. Let's say that I own these two pieces of land. Did you know that the Egyptians advanced a lot of math concepts because they were trying to figure out areas of land to determine how much to charge in tax? Since land is something that's usually not nice and square in real life, they needed to figure out how to calculate areas of triangular, trapezoidal, circular regions. So because of that, they developed a lot of area formulas, even without calculus. But okay. So if we're going to use calculus to calculate these two areas, we do need to figure out like some critical points here. Like, for example, this point, this point, this point, this point, they all seem very important, right? And some of these we can just figure out visually from the graph. So let's see, like this point is 0, 2, right? And this point is 0, 0. And this point is 2, 0. And this point is 2, -2. So the big mystery point is like this point here, right? And once we figure out this point here, we'll call it A for now, then we could do an integral to calculate this total area. And unless we're doing it with a calculator, we do need to divide it up into two separate integrals. And one of the integrals would calculate the area of this portion, okay? And then the other integral would calculate the area of this portion here. And to do the integral, the really important x-coordinates that we need, and we only need the x-coordinates, are going to be this one, and this one. The y-coordinates you really don't need to do the integral, and the reason why is because if you write the integral, you need two x-coordinates. One of them goes here and one of them goes here. And let's do this region 1 first. So region 1. So in region 1, the x-coordinates you're going to use are the starting coordinate, which is 0, and the ending coordinate, which is this one. We don't know what it is yet. Okay? And then what do you put in here? Why do we not need to know the y-coordinate? Because we're going to put in the function here for y, -x² + 2. And so the y-coordinate is like automatically figured out for you at every single x. And as you can see, the y-coordinate actually varies according to what the x is, right? It's getting steadily lower and lower. So you can't just put in y = 2, because y = 2 only for this leftmost long thin triangle. As you move to the right, it gets smaller and smaller. So you do need to use a varying expression to figure out the height of each one of these little rectangles you're chopping it up in. When you're doing the integral, you are chopping it up into little long, thin, vertical rectangles. What is the width of each one of these rectangles? Well, eventually it kind of approaches 0, but you can't put 0 in there, otherwise you're going to multiply by 0 and everything's going to be 0. So what you do is you represent that ever-shrinking width as dx. And dx is the width of one of these triangles. It eventually approaches 0. So we use that here. So basically what you're doing, the integral is saying, I am taking a bunch of long, thin rectangles from the leftmost position, which is 0, and the rightmost position, which we haven't determined yet. The height of each rectangle is -x² + 2, and the width of each rectangle is dx. So if you were going to draw it, it would look kind of like this. Okay, so this is a little rectangle, long thin rectangle, width dx. The height is negative x squared plus 2. And then the actual x coordinate, varies. It varies from 0 to a. Okay. And why are we dividing these two regions up into these two regions up? Because this first region, you can see that if we calculate the area of this region, it's going to be a positive number. And if we calculate the area of this second region, it is going to be a negative number because it's below the x-axis. And if we're going to tax these two land pieces, we want to tax them both as positive regions and add them together, not subtract out the second piece from the first piece. So we do need to do an integral separately for each piece to make sure that we get a positive area for each one. So now that we've said many times that we need the value a, let's figure out how to get it. Well, remember that this coordinate here is a comma 0, right? What does that mean? That means when the x is a, the y is 0. So let's put 0 equals negative x squared plus 2. And then let's figure out what x is. So we're going to subtract 2 from both sides. We're going to get negative 2 equals negative x squared. Make both sides positive by multiplying both sides by negative 1. We get x squared equals 2. So x is equal to square root of 2. Okay, so our a turns out to be square root of 2. Alright, so now everywhere we said a, we can put in square root of 2. Is that it? Oh, here. Put the square root of 2 here. Okay, now let's figure out the this quantity. So, and since we do have real number limits, 0 and square root of 2, we're actually going to get a real number answer here. And remember, we're only calculating region 1. So to calculate this, the next step is we look at this and we have to take the integral of this inside expression. It's actually a pretty easy integral, right? The integral of x squared is x cubed over 3. The negative simply follows it down here. The integral of plus 2 is plus 2x. What's the notation we're going to use here to show that we have taken the integral, but we have not evaluated the limits yet? What we do is we put the integrated expression inside. You see that this is not the same as the other expression because we've taken the integral. We put it in between these two brackets. This is like the book's notation. It's not the notation I used in high school or in college, but it's the one that you should use. So you're going to put it within brackets, and then you're going to put the same limits from here, 0 to square root of 2, you put them over here. And please use this notation because the IB examiners are looking for this. This may be 1 point if you write this correctly, and it's pretty easy, right? Okay. So now what do? You are going to evaluate this function 2 times. One time you evaluate it with the limit square root of 2. One time you evaluate it with the limit square root of 0. And in between, you're going to subtract the 2. So let's, and make sure you put them in parentheses because especially this expression here, since you're subtracting, some people get confused on distributing the negative sign. So be really clear about this too. So we're going to put square root of 2 in there. So we're going to put negative square root of 2 cubed. And the negative is outside the cubed. And I'm not going to explain that now. Hopefully you understand what that means, but if you don't, talk to me. And then when you put 0 in, you're going to get 0 cubed divided by 3, negative, which is just 0, and then you're going to have plus 2 times 0, which is just 0 also. So the second term is just 0. So when you rewrite what's here, you're just going to have, let's see, Square root of 2 cubed is the same thing as the square root of 8, which is 2 square root of 2 divided by 3, negative. And then you have plus 2 square root of 2. You can combine these by putting them over a common denominator of 3. So that would be 6 minus 2, 4/3 square root of 2. Okay, so this would be your answer here. Alright, that's for region 1. What would you do for region 2? Well, region 2 has the same integral. The only thing that's different, and so I'm going to put the integral, negative x squared plus 2 is the inside, right? The only thing that's different is the limits of integration and also the sign here. So the limits of integration are going to be the square root of 2, 2, 2. Okay? Now what's the problem? If we do the integration from square root of 2 over 2, it's going to give us a negative region. The answer is going to be negative. And we want it to be exactly the opposite of the negative answer it's going to give. So one thing we could do to do that is we could put a negative sign here. And then that would give us a negative of that negative region. Since we know the answer is going to be negative, we put the negative sign here so we can make that region a positive region. And the rest of it is the same. We are going to take the integral of the inside, which we've already done above, so you don't need to redo that work. You could just copy it down from above. It's negative x cubed divided by 3 plus 2x. And then remember the notation. We're going to write 2 and square root of 2 here, and then we need to put this negative sign that's here. We need to put it here also. So you could use this negative sign to invert what's inside here, or you could take a negative of the answer after it's already done. Let's do that. We'll take the negative of the answer after it's already done. So we're going to evaluate this expression 2 times. One time we evaluate it with 2, the other time we evaluate it with square root of 2, and we're going to subtract the 2 from each other. So this first one we put negative 2 cubed, which is 8 again, and this should look similar to the other one, except it's 2 instead of square root of 2. And then this one is going to look exactly like what we got before. We're going to have negative square root of 2 cubed divided by 3 plus 2 square root of 2. Okay, and then the rest of it's just algebra. Minus 8/3 plus 4. And, you know, even if you get this part wrong, as long as you did everything right and you showed all your work, you're only going to miss like 1 or 2 points on the problem. So not like it's going to be fatal. Let's see, square root of 2 cubed. Square root of 2 cubed is 2 cubed, which is 8 square root. And remember, square root of 8 is the same thing as 2 square root of 2. So again, we have the same thing we had before. 2 square root of 2 minus 2/3 square root of 2, and then we can go back up here and get the answer. It was 4/3 square root of 2. So we got 4/3 square root of 2 for this second part. The first part is going to be a nice number with no radical. It's going to be 12/3 minus 8/3 is 4/3. Okay, and so we have 4/3 minus 4/3 square root of 2, which is going to be, 4/3 times 1 minus square root of 2, but then we're going to take the negative of that, so it's going to be 4/3 times square root of 2 minus 1. And so this is going to be 1.414 minus 1 is 0.414 times 4/3. It'll give you, a decimal answer if you multiply it out. Okay, so that's how you would get, each of these, the areas for each of these two pieces. And I went really slow and broke it down, and hopefully you followed that, and maybe it'll help you get it straight in your own mind. But you can see that, there's not a lot of difficult concepts here. Maybe it's maybe like 4 or 5 small concepts that you need to remember. It's like, what do you use for the limits? What do you put inside the expression? How do you take the integral? What is the book notation to show how to take the definite integral, what this dx means at the end, what this represents in terms of this little rectangle you're looking at. Be careful when you are doing the algebra here because there's a negative sign that's distributed, and that confuses a lot of people. So, there's just like, maybe 5 small things altogether which make this challenging, but a lot of these small things you have done in previous chapters. So don't forget what you've done in previous chapters when you learn this problem. The only thing different between this problem and what you've done before is maybe the part about the negative areas that you want to take the opposite of those. But I think that's pretty much it. Everything else we've done in previous chapters. So get straight what you learned in the previous chapters and just add this little bit on afterwards.